This is the third physics lab where we studied a black hole and how to model it with a computer. So for the introduction, we coded for a star's trajectory that is orbiting around a black hole, and then we analyzed the star's motion to find the net force as well as its parallel and perpendicular components. So after all these calculations, we were also able to estimate the mass of the black hole. Some of the equations that we studied in this lab are F net is equal to F parallel plus F perpendicular, and then the change in momentum over time, net, equals the parallel and perpendicular components, where the parallel component is equal to the rate of change of momentum over time times p hat, plus the magnitude of the momentum times dp hat over dt. So an example of these parallel and perpendicular components could be seen here with a planet orbiting the sun. The planet's velocity is the f parallel because it's going parallel to the motion, and then we have our f perpendicular facing inward since it's curving motion, and your f perpendicular component will be facing into your kissing circle. So for the Glowscript code for this lab, we can see it right here. There's several lines that I had to change. First of all, the seed up here, which generated the trajectory of the star, is my GT email. And if we scroll further down, none of this code had to be changed, but we have our g, gravitational constant, and then the star's mass, which was given to us, which was 2 times 10 to the 30th, and then the delta t, which is just the amount of, or the number of seconds in a day, so 60 times 60 times 24. And as we scroll further down, we have our v initial and v final, which were calculated for us, and then to find the initial and final momentums, all we had to do was multiply these velocities by the star's mass. Then to calculate delta v and delta p, we just had to subtract final from initial values. And then to find the rate of change of momentum, we just had to divide delta p by delta t. Then we could also set the f net equal to dp over dt, since these quantities aren't the same, but they do have the same direction and magnitude. Then to calculate p hat, we had to just divide the initial momentum by the magnitude of the initial momentum. And then to calculate change in momentum or change in time, we just calculated p final minus p initial and divided it by delta t. Now we could calculate our parallel component of our rate of change of momentum, which was just these two quantities multiplied. We can also set the parallel component of force equal to this, since they have the same magnitude and direction. To calculate the perpendicular component, we just subtracted the parallel component of the change in momentum from the total change in momentum over time. And we could also set this equal to the perpendicular component of force. Then all we had to do was change some of the arrows to make sure they showed up clearly on our image, so we can see our arrow scale had to be made quite large for them to be visible. And then we could print the f net parallel, and the f net perpendicular for each moment of the star's trajectory. Then on the bottom here, we were able to calculate the black hole's mass by simply rearranging g m1 m2 over r squared is equal to our f net force, since the only force acting on the star was the black hole. So when we run this program, it looks something like this, where the blue arrow is our perpendicular force, the purple arrow, which is tiny here, is the parallel force, and then the f net is your orange arrow. So we can see when it was going around, our forces inward were much larger when we got closer to the black hole on the left, and then they got much smaller on the right. And we can see that the mass of the black hole that we calculated was 1.3 times 10 to the 9th kilograms, which is quite large and sounds about right for the mass of the black hole. So if we go back to our presentation, we can see these are all of the values that I had to change in my code. And then again, to calculate the mass of the black hole, we used this formula right here, solving for M2 since we knew all of the other quantities. So for the what does it mean question for this lab, it was asking to discuss the differences between net force and its parallel and perpendicular components compared to the rate of change of momentum and its parallel and perpendicular components. So the direction and values of all of these will be the same, and they'll be pointing in the same direction and be the same length. However, net force is the sum of all the forces, while the rate of change of momentum comes from an analysis of the object's motion. So they come from two completely separate things. If you know force, you can update your change in momentum, and you could do the same thing backwards. However, they're certainly not the same thing, even if they have the same direction and magnitude. For the what if question for this lab, it was asking if the black hole was removed and a new black hole was placed, but the motion of the observed star remained unchanged, and it was only affected by the gravitational force of the new black hole, could we find a value for the mass of the new black hole? And the answer to this question is no, it would be impossible to find this mass because the original mass was calculated using only the motion of the observed star. We used no other data. So if the motion stays exactly the same, then all our calculations would end up being the same, and the calculated mass of the black hole would also remain unchanged. This was my Physics Lab 3. Thank you.